Welcome to Study Loop.
So we are dealing with diffraction here. The width of the aperture is 0.24 millimeter. The wavelength incident is 540 nanometers, so within visible range. And it falls on a screen at a distance of 3 meters. Now, if you want to find out the distance at which we see the first minima, let's call this angle theta. Now, if this distance is x, now because angle theta is very small, we can write that theta is equal to x by the 3 meters, which is the distance between the screen and the aperture. Now, we know that for diffraction, sine theta is equal to m lambda by d. And for order 1, it's simply lambda by d. So now because theta is very small, we can see that sine theta is almost equal to theta, which gives us x by 3 meters is equal to lambda by d. So x is equal to 3 into 540 nanometers divided by the distance, which is 3 meters. I'm sorry, d is the aperture width, so that is 0.24 millimeters, so that's into 10 power minus 3, which makes x 6.75 millimeters. Now that we have this, we want to find out the intensity at the point midway. Now, for point x by 2, let's say the angle is alpha. Now, x by 2 would be alpha times the distance, that is 3 meters, which gives us alpha is equal to pi by 2. Now, we can simply say this because we remember that the intensity formula is I naught sine beta by 2 by beta by 2 squared. And the first minimum happens when beta by 2 is equal to pi. So midway between that point, beta by 2 must be equal to pi by 2. That is all. So now that you have that, we know I is equal to I naught sine pi by 2 by pi by 2 squared. We know that I naught is 6 into 10 power minus 6 watt per meter square times sine pi by 2 is 1, and 1 by pi by 2 square is simply 4 by pi square, which becomes 2.43 into 10 power minus 6 watt per meter square.